Hello everybody, welcome to this video introducing trigonometry. So trigonometry, trig is 3, okay? Trigonometry deals with triangles. So as is a tradition in mathematics, let's introduce triangles by talking about something totally different. Okay, so let's begin with a circle. And we'll put some axes on the circle too, just to make things a little bit easier to work with. Now, this circle has a very special property, okay? This circle has a radius equal to 1. Okay? This circle has a radius equal to 1. Now, if you look at where this radius intersects the circle, we could have drawn any radius on, okay? So if I just take away that, okay, we could have drawn our radius there. We could have drawn our radius here. We could have drawn it here. Close enough. We could have drawn it here, or here, or here. We could have drawn it anywhere. But for the meantime, we'll just keep it here for some just simplicity for the time being, okay? Now, what separates all the different radii that I drew just then was this angle here. This theta, this angle here is different. If I were to, for example, put a radius here, then of course that angle would change. Or if I drew the angle round to about here, then this angle, radius would change. So that's our variable, if you like. Our radius is going to stay the same, but it's our variable, i.e. the angle, that changes. Now, for every different radius that I drew, as you can see, where this line attaches to this circle, we have two lengths. We have this length and this length. This length is the distance from the x-axis, and this length is the distance from the y-axis. And as you can see, as we change this theta, these lengths will increase or decrease. So if we represent this length, let's do this one in red, and this length, let's do this one in green, then what we have is something that more or less looks like this. We'll call this D1. This is our first distance that we drew. So we have D1, which of course depends on theta. That's what this means. This D1 depends on theta. Those who are more used to functions, you'll know that this is D1 of theta. That's how it would be said, but just for the time being, it suffices to say that this measurement, this distance D1, this length here, depends on theta. And similarly, this D2 of theta, this distance 2, which depends on theta. Theta changes, and therefore D2 changes. The theta is the independent variable, okay? Theta varies independently. It doesn't really matter. We can do what we like to it. And D1 and D2, these are our dependent variables. These measurements depend on what theta is. So let's do one more thing. I'm going to just redraw this diagram a little bit, okay? And as you can see, what we have now is a triangle. Now thankfully, we can start using a little bit that we know about triangles and annotate our triangle up here. We have our hypotenuse, our opposite, and our adjacent. And then we can start marking on some variables. How long is the hypotenuse? Well, if we look at our triangle here and our triangle up here, we said that this circle has a radius equal to 1. And therefore this length here, this hypotenuse, is the radius. And so is equal to 1. And as we said here and here, these lengths depend on what angle we choose theta to be. So we can rewrite. Okay? So we know that these lengths will change depending on where we put theta. Just to show you, if I just get rid of this for a moment, this d1 of theta is a lot longer than it was previously. And this d2 of theta, this distance 2, is a lot shorter. So, drum roll please, I'm going to tell you what these lengths are, and you might be familiar with this, and you might not be, but don't worry if you're not, because my job is to explain it to you. So this d1 of theta, this is equal to sine of theta, and d2 of theta is equal to cosine of theta. Sine, cosine, they come from the Greek words meaning curve, I think. Don't quote me on that. So we have we have sine theta, cosine of theta. If you remember, you may or may not have come across this yet, but you can already calculate these sine theta, cosine of theta by using the following formulae. We have that sine of theta is equal to the opposite divided by the hypotenuse, and we have that cosine of theta is equal to the adjacent divided by the hypotenuse. These are the more general forms. If you were asked, for example, if you were given some random triangle and asked to calculate what these values were, you'd be able to do that very simply by taking the length of each of these, the length of the opposite divided by the length of the hypotenuse, and of course the same for adjacent and hypotenuse. But that's the easy stuff. This stuff is actually a lot easier, because look carefully, how long is the hypotenuse? Well, it's equal to 1, isn't it? So this just becomes O, which is sine of theta. Now that might seem a little bit daft to you, but actually what I've done is just proven that this length, red length here, when our triangle has a hypotenuse of 1, or in other words, if our triangle is inside this unit circle, this is equal to sine of theta. And again, for the cosine of theta, we have just cosine of theta. Now, you might be wondering, what about if our circle doesn't have a radius of 1? Well, actually, that's okay, because it still doesn't matter. And I'm going to do this in blue. Let's choose sine of theta, for example. So we know that sine of theta is equal to opposite over hypotenuse. But what happens if we scale? That's what we're asking. We're being asked to maybe scale this triangle, make it smaller, make it bigger. Okay? So if we do that, if we scale this triangle up, then what we'll have is we'll choose some scale factor. Let's choose alpha. Alpha times O divided by alpha times h. Alpha times h is easy to see because h is the hypotenuse and also the radius. If we scale this circle by some factor alpha, then this hypotenuse will also scale up by alpha because it's just the radius. And the same thing happens for sine of theta. This length will get longer by some alpha because our radius has gotten longer by alpha. And what happens? Well, these alphas just cancel out and we still have sine of theta. The reason that we use a radius equal to 1 is because of this property here. And therefore, when we start multiplying the circle, expanding and contracting the circle by some scale factor alpha, it doesn't matter. Because, as I said, we always come back to this. And of course, the same happens with cosine of theta. And lastly, the intuitive, if you like, not forget the maths for a moment, the visual intuitive definition of sine of theta and cosine of theta are the lengths. This length here, this is sine of theta, and this length here is of course cosine of theta. And lastly, we'll look at one more property. Take our right angle triangle, or a reasonable facsimile of a right angle triangle. We know that this length is equal to 1. I should have said this case specific right angle triangle. The radius is equal to 1. This is sine of theta, and this is cosine of theta. But by the Pythagorean theorem, we know that a squared plus b squared is equal to c squared. So again, let's start substituting in. 1 squared is equal to sine theta squared plus cosine theta squared, which implies that sine squared theta, we write it like this with the power up in the middle. We tend to do that with any functions that are words. So natural log ln would be ln squared x, sine squared x, etc. Plus cos squared theta is equal to 1. And again, this works for any scale factor, because alpha squared is equal to alpha squared sine squared theta plus alpha squared cos squared theta. And then we just divide by the alpha squareds and arrive back to this equation.